Capacitors are a class of electrical devices that are extremely useful in electronics, for instance, or other applications due to the capability to store potential energy under an electric field. So we have a charge acquisition due to an electrostatics process that leads to the formation of potential difference and a localized electric field. Basically, capacitors are devices that, with respect to batteries we know are characterized with a high specific energy but quite low specific power. In the case of capacitor, we have a huge specific power but a quite low specific energy. But from the other hand, the capacitors can be limited in the power achievable only due to the resistance of the dielectrics with respect to certain potential. At the same time, so with respect maybe rechargeable secondary battery, capacitors are characterized with a really major and huge number of cycling of charging-discharging cycle, and so are extremely stable device. Basically are used a lot, for instance, in order to modulate some pulse of current and homogenize it in different circuits. So now let's focus our attentions about what is the structure of a capacitor. So we have defined basically the main characteristics and the main difference with respect to batteries. But a capacitor, having a high specific power and high number of discharging cycle, but good aspect, but negative aspect, we have, for instance, a quite pure or low specific energy. So these are the main characteristics, the pros and the cons of the use of this device. But now, why we can say that we have this high specific power and this pure specific energy? It depends basically on the mechanism on which the charge is acquired in capacitor. So capacitors are able to store energy due to the acquisitions of charge on the plate of this instrument due to an electrostatic process. What does it mean? So capacitor is composed of two plates. If we are looking now at the most common situation, a plate capacitor, two plates of a conductive material separated with an insulant, a material that is not able to conduce electricity. So for instance, these two plates could be a metal in general, and we have an external circuit here, and what is happening is that in the moment in which we are applying a certain potential difference, maybe we are connecting our capacitor to a battery that is something able to provide a continuous electromotive force, is able to provide a potential difference. So this battery can ensure movement of electrons in the external circuit, and in the moment in which we are closing the circuit, so the current start to flow, the current flow in the opposite direction with respect to the flowing of electrons to the convention, and we have the negative charging of this plate and the positive of this one. So basically what is happening is that we are negatively charging this plate, and from the other hand we are positively charging this one. So the electrons are entering here and are asking from this plate. What is extremely interesting is that inside here, since we have an insulant, it could be vacuum or a material known as dielectric. So it could be, for instance, ceramic, it could be glass, it could be even air or plastic. And so basically we have a structure that is composed of two metal or conductive plate, in between we have this dielectric or the vacuum or something which is not able to conduce electricity. For this reason, even if we are closing the circuit and actually a real current is flowing, we cannot appreciate the passage of electrons here. So here we do not have electrons. Electrons enter here and are escaping from here, but without passing inside this zone. Basically what is happening is that under this potential difference, this dDp induced by the cell, we are charging one plate and we are charging the other one. This means that we are creating a potential difference and an electric field. So an electric field is created inside this zone that is localized. And basically, since we are creating an electric field, we have a potential difference, we have also an energy that we are storing. We are storing energy due to the creation of this static electric field. We have the creation of, we have the storage of potential energy due to the creation of an electric field. And if we are running our process for a sufficient long time, what is happening is that we are charging more and more this plate, and so we are charging more and more this plate with the opposite charge, and we are charging it until a point in which the difference in voltage, it will be equal with respect to the one of the battery, but opposite, and so the flowing of charge ceases, the flowing of electrons stops. So we will see also this, speaking about the equations able to describe the chargings of a plate capacitor and even the dischargings, really interesting, for instance, in a RC circuit. And what is important is this, that we have no real involving of the bulk, a real involving of what is in between the electrode. So the storage of energy involves only basically the electrode, the surface of the plate, and this is the reason for which, even if the power is extremely fast, since here we do not have any types of chemical reactions and obstacles to a chemical reaction, because we know, for instance, in the case of overtension or in general, how much problems we have in the moment in which we are running an electrochemical process, in which we are using a reaction for produce energy. We have a lot of obstacles that we need to overcome, and for the reason a battery is it's not able to provide the energy inside itself really quickly. But from the other hand, we have a huge amount of energy, because in battery the reactions involves also the bulk. Also the bulk of our batteries is involved in the storage of energy. In this case, not. In this case, the energy is storage involved only the presence of plate. And this means that we have high specific power, because the process is electrostatically and not vertically, but from the other hand, we have a pure amount of total energy. So in general, we can say that the amount of charge that can be acquired on a plate, it depends on the total voltage that we are applying. For instance, the voltage that we are using with the battery. If we use a battery as a fuel cell having 0.6 as voltage, we can have a pure charging. Maybe if we are using a lithium-ion battery that can even reach an output voltage equal to 4 volts, well, we are expecting to have an higher charging. So we have that the amount of charge collected on the capacitor is proportional to the voltage. And to the type of capacitor, in which way? We need to introduce a parameter that is able to quantify for a certain capacitor in which way increasing the voltage means also increase the charge. And this parameter is the capacitance. The capacitance that is equal to C measured in farad is equal to the charge over the voltage. What does it mean? That, for instance, if we have a capacitance of 1 farad, we are able to obtain 1 coulomb of total charge on one plate by applying 1 volt. If the capacitance is higher, by applying the same voltage, 1 volt, we are expecting to have an higher charging, more than 1. And the capacitance basically literally tell us how intrinsically our capacitance, this is a function of the material, is a function of the shape, the geometries, basically tell us in which way, by applying a voltage, we are able to charge this parameter, but we know that the capacity is basically a function of the charge, and so is the function of the electric field, and so is the functions of the energy. Having an high capacitance means have, with the same dDP applied, an higher capability to store energy. And in particular, it's also extremely interesting to connect the capacitance with the geometrical parameter of the capacitor. And we can say that the capacitance, in this case, is equal to the area of the plate over the distance between the two plates for the permittivity of the vacuum for the one of the electric. So basically, what does it mean? That if we have a higher permittivity of, so a better material as the electric, we are also able to get close the two different plates, and if we increase the area, this could be an extremely interesting topic, the reasons for which sometimes we are using electron composed inactivated carbon in order to improve the total area. What is happening is that we are increasing the capacitance, and so we are increasing the capability to store energy by applying the same dDP. So in this case we have defined basically what is the capacitance and the two different main formula for these types of parameter. But now it's also important that write here capacitance. It's also important to look at how it's computable and how we can calculate the total energy stored. The total energy stored, we know, is a function of the charge accumulated, and so it's a function of the electric field created and in general the potential. But how it's possible to know this? Well, we can say that the total energy stored, it could be defined as the work necessary to move one charge against the electric field. So it's the work for move one infinitesimal charge element versus the electric field. So if we are imagining to take an infinitesimal, for instance, dq plus charge, an infinitesimal positive charge element, we want to push this charge from the positive plate to the negative one, fighting the electric field, where the efforts required in order to do this action, the difficulty in order to take this and move fighting the electric field is obviously a function of how much strong is the electric field. Stronger the electric field, more important the effort in order to take this charge and move it against this electric field. But obviously, if the electric field is stronger, it means that we have a higher voltage, it means that we have a higher amount of charge, it means that we have stored more energy. This is why we can say that the total work in order to move one charge against the electric field is a means of how much energy we have. Because if we have more energy, we have a stronger electric field, and so we need to do more efforts, and so the work it will be higher. So higher the energy, higher the efforts, higher the energy, higher the work for this action. And in particular, from a mathematical point of view, we can say that the infinitesimal work is equal to the integrate between 0 and the total amount of charge at full charged capacitor for the voltage, obviously, and dq. Now the voltage could be connected with this equation, and we can rewrite this as a function of the charge over the capacitance, and so we can say that this is equal to this q squared over capacitance. But at the same time, also proceeding with substitution, we can say that the total work, the integrated work, so the energy stored inside the capacitor is equal to this for C, for this. And so what does it mean? That if we want to increase the total energy of our capacitor, we can act on two parameters. The voltage, so maybe we can just use a different types of source, But this means that we need to change the battery, and it's an hazard, it's a risk. Why? Because if we are exploiting a too strong voltage, we can break down the dielectrics, and this is a problem. From the other hand, we can in a more smart way act on the plate of the capacitor. So we are acting on the capacitance. In which way? Maybe we are changing the material. Maybe we are changing the shape, the geometry's parameter. And so acting on the capacitance, we are able to improve the energy stored inside the capacitor. So, and after describe this, it's important to say that there are different steps of capacitor that are known as supercapacitor. But what is a supercapacitor? A supercapacitor is basically a particular type of capacitor built with specific characteristics. So not a capacitor anymore, but a supercapacitor that is something in between a battery and a capacitor. Basically, a supercapacitor is a capacitor with a very, very high capacitance. So high capacitance. We are speaking about a capacitance that is around thousands of farad. So we have thousands of farad. And also is, even if the capacitance is really higher with respect to a normal capacitor, we have that the voltage, the maximum voltage, is often a little bit smaller. But in general, we can say that the total energy, the specific energy of a supercapacitor is higher than the specific energy of an electrostatic conventional capacitor, from 10 or 100 times. So this, the specific energy of a supercapacitor, is 10 and up to 100 times higher with respect to the energy of a conventional capacitor. This basically means that we are able to store more energy and we are getting more close to the behavior of battery. We have, obviously, the power is still remain higher, but we are improving the energy, and so we are getting more close to the battery. We are in between with a supercapacitor. But from a real point of view, a supercapacitor is composed in a different way with respect to a conventional electrostatic capacitor. So in an electrostatic capacitor, we know that we have our metallic plate, our conductive material plate, and we have the dielectric, the vacuum, or the dielectric, the insulant. But in a supercapacitor, we have two different types of situation. We can have or an electrochemical electric double layer capacitor, or an electrochemical hybrid pseudocapacitor. So let's focus on the first one, the electrochemical double layer supercapacitor. So the electrochemical double layer supercapacitor is composed, as also in this two situation, two conductive plates this that is negatively charged and this is that is positively charged under the application of a potential difference. So the same situation previously done. So here we are imagining to have an external circuit. Let's design it. So we have our external circuit, our battery, maybe a lithium-ion battery. We have here that we are charging this plate negatively, and here we are charging this plate positively. So, in this way. But what is the difference between an electrostatic capacitor is what we have here inside the two plates. Here we do not have any more of the vacuum or the electric, but we have an electrolyte. It could be a solid or it could be a liquid. We have described in one of the first lessons again focus on the theoretical base of electrochemistry. What is an electrolyte? And in general, basically, this is an electrolyte in which we have some ions, some cations, and some anions with a negative charge. Obviously, that are statistically randomly distributed in each single point when the circuit is open. But when the circuit is closed, what is happening is that here we have the negatively charging and here we have the positively charging. And so these ions start to migrate, in this way. And from the other hand, the cations start to migrate in the opposite way, in this way. And so what is happening basically is what now we well known, because we have looked an entirely dedicated lesson about this argument. And so what is happening, if I recommend to see the dedicated lessons on the electrics double layer before look at these types of concept. But in general, what is happening is that we are collecting in a balanced mechanism the counter ion here. And from the other hand, we are collecting the counter ions here. So what we are creating is two electrical double layer. We have defined basically that there are a lot of different types of model, but in general, if you are simplifying the situation, we can say that each of these two singles double model, here we have, for instance, positively charged, surrounded with solvent molecules in the outer Helmholtz plane, and also here, please remember what we have described speaking about the double layer, and maybe between we have a single orientated water molecules maybe, or solvent molecules with low permittivity that is acting as something as the electric. What does it mean? That each single double layer is behaving as a capacitor. So with this particular electrolyte, we have something has two capacitor with respect to a single one. This means that we can store more energy. We are in a smart way just with using an electrolyte. This is an electrolyte and not the electric. An electrolyte. Obviously no current can pass here. We are only able to appreciate the movement of electrons. But we have the movements of ions, but we have this movement of ions that can ensure the creation of a double layer here and double layer here. And these two double layers can act as two plates capacitor, and we can store much more energy. And this is for what concerns the electrochemical double layer capacitor. It's important to recall, for instance, the double layer. I have done a specific lecture dedicated on these topics before understanding this concept. And then we have the last types of supercapacitor, that is the electrochemical hybrid supercapacitor. In this case, basically, it's important things. Previously, I missed to say that in a supercapacitor, also in electrical double layer, the electrodes are often composed of activated carbons. And this is due to the fact that in order to increase the capacitance, that is always something that we want to do in order to increase the energy stored, it's important to maximize the contact and the surface area between the electrolyte and the electrode. And this is the reason for which we are using often for the generations of this plate a base that is a current collector, a common metal maybe, but on where it we are depositing some activated carbon, because in this way we are able to improve the surface area. Well, in this case of the electrochemical hybrid capacitor, this is something that is extremely close with respect an hybrid situation between a battery and a capacitor. Because in this case what we are doing is building a capacitor that is characterized with one electrode that stores energy electrostatically and one electrode that stores energy faradically. What does it mean? That this electrode, for instance, the plate that is positively charging, is nothing different with respect to what we have described in a double layer capacitor. So we have basically also in this case an electrolyte inside between the two plates, and this electrolyte lead when we are applying a potential difference connecting our capacitor to a battery, so a potential difference, we have the migrations of cations and the well-known double layer. So, for what concerns the positive, for instance, electrode, this plate, we have the same behavior in an hybrid capacitor that we have described in the electrical double layer. So also in this case, again, we are storing energy due to an electric field created between this charge and this one. What is difference is the negatives, or in general the other type of electron, in this case the negative, because in this way we are basically storing energy as in a battery radically due to reactions. For instance, often one of the classic example is the lithium-ion supercapacitor or lithium-ion capacitor. That is a particular type of supercapacitor in which we are able to obtain a great output voltage and at the same time quite important specific energy, and so a huge specific power and important specific energy. And this is due to the fact that we are using a carbon materials electrode pre-doped with lithium cation in order to pass from an electrode potential from 0.1 volt to minus 2.8 and minus 0.1 to minus 0.8 or even minus 3.8 volt, and so increase a lot the output voltage, since we remember the output voltage is basically the difference between this potential and this one. Higher is the capacity to decrease the potential of the negative pole, higher it will be the output potential. So basically, without stressing you too much, what is important in saying that the electrochemical hybrid supercapacitor are capacitors that are meeting together one component that is basically the component of a battery, for instance a lithium-ion battery, and from the other hand a component that is typical of a double layer supercapacitor. So we are basically in this way creating something that is exactly in between a battery and a capacitor.